in the now we're on record.
Yeah.
I think bubble walls redshift like tomato. Right? Bubble walls redshift like tomato walls. So you need to worry about.
Yeah,
Okay.
it all happened, it completes pretty early.
Okay.
Thanks. Okay, I guess we can start then. We're very happy today to have Soubhik telling us about CMB hotspots and early galaxies. Please take it away.
Am I visible over Zoom? Visible and audible over Zoom, I guess. Okay. All right, great. So thank you so much for having me. It's a real pleasure to be back here. Yeah, today I'll be talking about certain rare processes that could occur during inflation, and I'll talk about some of the cosmological implications. For example, I'll show that these processes, they could give rise to localized hotspots on the cosmic microwave background, and they can also modify the formation of galaxies. Like they can, for example, give rise to very high redshift galaxies, which would be at higher redshift compared to lambda CDM expectations. So the CMB part of the story would be based on the first three papers here, and then the discussion in the context of galaxies that's ongoing with Neil at NYU. All right, so of course we know a lot about the early universe based on the precision cosmology that we have as a field have carried out over the last decades. For example, the cosmic microwave background anisotropy is here is, for example, an image from Planck, and also the large-scale structure distribution of matter and galaxies around us. Both of them, they have given us very precision constraints on a bunch of different parameters. They have constrained various BSM scenarios, and overall, these are really a treasure trove of information. And predominantly, like the way we have analyzed this cosmological data is that these are in some sense sort of random fluctuations, and the way we have tried to analyze them is we have tried to construct various correlation functions. So asking whether two distant points on the sky, whether they are correlated with each other or not. So that's like looking for a 2-point function. And then we have also done it with the 3-point and 4-point correlation functions, especially in the context of the CMB. And then these kind of studies, they're also taking up and they're gaining momentum in the context of large-scale structure. And overall, from these observations, from these searches, we have a reasonably good idea regarding what the primordial perturbations were. So far, we have not detected any isocurvature mode, so we believe the perturbations were adiabatic. They're also approximately scale invariant, so no funny features on the spectrum yet. And they're also Gaussian to the degree we can tell. Okay? So these are the information that we have gathered from making these observations and carrying out these searches. And very roughly speaking, if you were to sort of summarize this in a cartoon, if you were to draw the probability distribution function of the primordial curvature perturbation, you would say it's just a Gaussian field, and you just sample from this Gaussian field, and eventually you let the universe evolve, and that would give you the CMB and large-scale structure, which are also approximately Gaussian. Okay, but as I'll show in this talk, there can be processes, rare processes during inflation, which can modify the PDF. So for example, along with the standard contribution, which is shown in blue, there can be this dashed red contribution from some new processes. And that would, of course, make the entire PDF non-Gaussian. right? So if you were to add the red and the blue. So of course, this is a non-Gaussian contribution overall, but the question I would like to ask is, the way we have been searching for non-Gaussianity, which is through this 3 and 4 point correlation functions, whether they are optimal or they're enough to capture this type of a deviation. So that will be kind of the overarching question that we'll be coming back to throughout the talk. And of course, like first I would like to clarify, like in some sense, the first question you could immediately ask is, why would we have such a modification? Like, what is the microphysics that can give you a bump like that, for example? And very generically, you might expect that, like, maybe there are some rare processes, maybe something associated with phase transition, maybe something associated with particle production, that were happening pretty rarely during inflation, and they were happening on top of some ambient Gaussian fluctuations. So because these were additional to the random Gaussian field, they could potentially give you bumps like that. On a very qualitative level, I mean, it could happen from a different types of microphysical scenarios, but in this talk, I'm going to focus on a model of particle production, and we'll see that this model would actually predict a type of deviation as shown by the red dashed line. So that would be our concrete model involving some cosmological particle production or inflationary particle production. And we'll see that it would motivate carrying out new types of searches, both in the context of CMB and also structure, both like large and small scale structure. And in some sense, these searches, depending on what the Hubble scale during inflation is, these searches could be sensitive to particles that are extremely heavy as the gut scale, which could be around 10 to the 16 GeV. So that's kind of the broad idea. And with that in mind, here's the outline for the rest of the talk. So as I said, first I'll focus on a model of inflationary particle production, and we'll see that these kind of scenarios, they can give rise to localized overdensities in the primordial density field. In some sense, they can give rise to a 1-point correlation function of the curvature perturbation. And then I'll sort of evolve those overdensities in time and first ask, how do they affect the CMB? We'll see that these overdensities, they can give rise to hotspots on the CMB. So very sort of bright localized regions. I'll compute how bright those regions should be, how do they actually look like, so their shapes, for example. And then I'll describe a search that we did with the Planck data, looking for these bright spots or hotspots. And then I'll move to, if you want, lower redshifts. So because these are overdensities, they would of course affect structure or how galaxies would form. And in particular, I'll show that they can give rise to galaxies at a higher redshift compared to what you expect from lambda CDM for the same halo mass, if you want. So I'll estimate what these properties are, and then I'll comment on some of the observational aspects, for example, in connection with the James Webb results that we have been getting for the last few years, and also some future surveys. So overall, that's where we'll be going. All right, so let's start with the model. So one in some sense one of the big outstanding questions in the context of early universe cosmology is the structure of the inflationary landscape. We do not know how many fields were present during inflation, how many of them were dynamical, how they talk to each other, for example. And in principle, this landscape, or this multi-field potential, if you want, could be fairly complicated. And as you can expect, if different fields are talking to each other, a very generic consequence is that masses and couplings of particles or field quanta, they can vary with time as fields move around on this landscape. And in general, the possibilities are enormous, like lots of things could happen, and this is something that we have been studying for a very long time, including people in the audience. What I'll do for this talk is that I'll imagine I'll focus on only one heavy particle or one heavy field out of this landscape, and I'll imagine that its mass as a function of time has some random sort of varying behavior. But what would be important for us is that there is some epoch in time, for example here, where the particle mass or the heavy particle mass passes through a minimum. Okay? The overall function could be arbitrary. We are not really sensitive to the overall structure, but the main physics would be like a lot of the physics can just come from the fact that the particle mass passes through a minimum. So one of the things you can do in the context of single clock inflation, or if you want where the inflaton, like there is only one field that is predominantly dictating the evolution, you can trade time with the inflaton field phi. So you can write the same figure effectively, where the mass is now varying as a function of the inflaton field. Okay, so as the inflaton field moves, the heavy particle mass changes. So let's just try to model that in a very simple way. So again, I have that figure. So now I have a scenario where the particle mass changes as a function of the inflaton field, but then there is some field value phi star around which the mass passes through a minimum. And then that means you can do a simple scalar expansion of the effective mass around this point phi star. Of course, you get some leading order piece. The second term vanishes because it's around some extremum, and then you have the quadratic piece, right? So just a very simple Taylor expansion. But that means if you were to write down the mass, like the Lagrangian or the potential term for the heavy field chi, then just by doing a very simple algebra, you will conclude that there is some inflaton independent piece, which is the first term over here, m phi star. And then there is some coupling that comes from the second term over there between the inflaton and the heavy field. Okay? So it's the second term that vanishes as phi passes through phi star. Okay. Just to simplify the notation a bit, if I can write this guy as m0, and I can write this entire combination as some effective coupling g squared, has to be positive, and then the rest like this. Okay, this is a very simple model where it just tells you that you always have some mass m0, but then when phi passes through phi star, this contribution vanishes, so you're only left with this. But when phi is away from phi star, generically this would give a larger effective mass to the chi particle. So we'll see that like there are three parameters here, like the m0, which is the mass at the minimum, the effective coupling, and then the field value of the inflaton at the time of particle production. But then that also controls the time or the horizon size when particle production happens. So I'll denote that by eta star, which is the horizon size at the time of particle production. Okay. So we'll see like these three parameters would basically dictate almost all the phenomenology. So that, I mean, both in the context of CMB and in the context of Galaxy formation. Any question so far about the model? All right. So very good. So you see, like just looking at this, as phi passes through phi star, the effective mass it changes pretty rapidly because this g square term it vanishes, and anytime particle masses changes rapidly, you can have cosmological particle production. And one very sort of cartoon way or a cartoon analogy here is that you can imagine, for example, having a harmonic oscillator, a quantum oscillator within some well. You can imagine that the oscillator is initially in some ground state, but then let's say you do a perturbation, like you change the shape of the well, you stretch it so it becomes wider, and you do it very quickly. You do it non-adiabatically, so that the wave function didn't get a chance to get adjusted, so it remains like this. But while this guy was the ground state of this potential, it's not the ground state of the new potential, but rather it's a combination of the new ground state and the new excited state. So what you would interpret is that because of this non-adiabatic change, you now have a harmonic oscillator which has some probability of being in the excited state. So there's an analogy, but it works reasonably well in the context of estimating the particle production you have from vacuum as a result of this effective mass change as phi passes through phi star. And you can use the standard if you want Bogoliubov techniques to compute the probability of particle production. And you'd get an expression like this. So there's some exponential suppression when the M0 is bigger than this cube. Okay. The reason you get an exponential suppression is because if you want, this controls how rapidly the mass is changing, where phi 0 is the homogeneous value of the inflaton field. So this dictates the rolling speed of the inflaton if you want. And if the mass, if the minimum mass is much bigger than that, it basically means that you do not have enough energy in the system to produce this particle effectively, so you pay a Boltzmann type suppression. Okay, so that's exponential here. But then this gives you the probability to produce a particle with some physical momenta kp, and you can just iterate over it to get the number density of these produced heavy particles. It of course carries the exponential suppression from before, along with some prefactors. So in this regime, it tells you that if you have a very heavy particle, by heavy I mean M0 square much bigger than this, then you typically produce only a few of these particles, but you nonetheless do produce them. And we'll see that these, like this is the example of the rare process I was talking about. Although this number is exponentially suppressed, it can have some observational impacts in the context of both CMB and structure. Okay. All right, so
Sorry, you want chi to be actually heavier than H?
yes, much heavier than H. Yeah. So usually you'd say if it is much like if the mass is m, there's some exponential suppression which is m over h. And the examples I'll be giving you, these masses are like 100 or 1,000 times larger. So it's a huge exponential suppression usually. But the difference here is because the effective mass here, it's dependent on how fast phi is rolling. So you're not relying on quantum fluctuations to produce this heavy particle, but you're relying on the rolling velocity of the inflaton phi dot. So that's why the suppression scale here is not Hubble, but rather it's phi dot. All right, so that was mostly about how many of these particles you would produce in a given volume. But now we can ask, let's say you have produced these particles, what do they actually do? So this case is interesting because in this particular context, again, because you have this coupling, you have this term, for example, you always have a coupling between the inflaton field and the heavy field. So what that ends up doing is that it sort of mediates a force between the heavy field and the inflaton. And you can imagine the heavy fields being, so they're pretty heavy, they're almost like classical particles that just coast along as the universe expands. And what they do through this coupling is that they can exert a force on the inflaton quanta, which are light, and they can slow its evolution down. It's like a drag force, for example. So I'll be showing equations in a moment, but this is just to give you a cartoon picture. So because of this drag, what will happen is that if you have a region where there are these heavy particles, the inflaton would evolve slower than usual, and that would mean inflation would end later in that region compared to other regions because you are slowing it down, okay? And that means there is a time delay that would happen wherever these particles are localized in a very sort of spatially localized sense. But in the context of, again, single quark inflation, if you have a time delay, that amounts to having a non-trivial scalar metric fluctuation, so a non-trivial curvature perturbation if you want. But then, because this time delay only happens where these particles are, this modification to the curvature perturbation happens in a very localized sense. So just to draw a picture here, if you are to plot gravitational potential as a function of position, then if you have a heavy particle at some coordinate location here, what you would find is that the gravitational potential away from that region is unmodified. So this is some usual number, like let's say 10 to the minus 5. But then around the location of this heavy particle, you have a modification. So I'm going to quantify how large the spatial extent is, but this is sort of the cartoon idea. So it is around this location where the inflaton was slowed down, and that's why inflation ended later, and that would eventually mean that you have more energy density in that location compared to the neighboring regions. Okay, so that means you have a localized potential well. Yeah.
Just to check.
Yeah.
So with particle production, I would expect there's some like friction because some of the energy from the velocity, the kinetic energy is going into. But you're saying this is a further thing of like a finite density effect then afterwards.
That's right. So the effect you're mentioning it's also relevant, and as you can expect, when m0 becomes smaller and smaller and becomes close to this, the effect is more enhanced because then you tend to produce more particles, and that sort of takes out more energy from the inflaton field, so it can actually slow it down if you want on a classical sense.
Yeah.
This one is, so I'm going to show you, let's go over to this slide. This is like almost like a Breming effect. So you have some particles which would Brem some inflaton quanta, and then these things would give rise to these potential wells I'm mentioning. But I'm getting a little ahead of myself, so let's back up a bit. So just to have another picture of what is happening, you can start with just the action of some classical particle. So it's a very simple action, dt times m, where m is the mass of the heavy particle. It depends on phi, the inflaton field. And so what you can do, you can expand it around some chosen value phi 0, and then the next term would be giving you something that's linear in delta phi, right? There will of course be more terms here, but those won't be relevant for this term. So now you see, like you have this effect, which is like a tadpole, which basically tells you that you should also look at the standard quadratic term for the inflaton fluctuations, and putting them together would basically tell you that there should be some sort of wave for the inflaton quantum. And if you drop in factors here, order on factors, you would conclude that this wave of delta phi is just given by this term m prime with some Hubble to restore dimensions. But in this given model, away from the time when particle production was happening, m prime is just this coupling G. So we had this G square, phi square, chi square term, right? So it's the same coupling G that would show up here. And that means the 1-point function is just determined by this coupling G, okay? Now, to compare all of this, you'd see like, so I'm going to again discuss this in more detail in the next slide, but if G is very large for some reason, then that would actually mean that your 1-point function is larger than Hubble, which is the typical size of the quantum fluctuations. But yeah, let me get to that on the next slide, but I'll just mention another thing here, which is this expression might be a bit surprising because I'm computing a 1-point function. And typically you always say, well, the 1-point function has to be 0 because of translation invariance. But here, the 1-point function is non-zero. And the reason is, wherever you have these particles, you of course break translation invariance around them. Like it does matter whether your translation direction has a particle in it or not. So in some sense, translation invariance, it sort of gets broken spontaneously once these particles are produced and in a sort of very localized sense. Okay? Another way to say this is this Breming effect I was talking about. So you have this tadpole term. What that means is that if you just imagine some geodesics of massive particles, there is some chance that they would emit an inflaton quanta, shown in this red dotted lines, and these inflaton quanta would eventually then perturb the late time surface you have. In other words, you get some sort of 1-point function wherever around the location of these particles, of these massive particles. So that in some sense is a cartoon description of what is going on. And you can of course back all this up with a more concrete calculation. But any questions so far on this picture?
Very naive question. Can you explain a little bit Can you explain again why inflation would be delayed? The ending of the inflation would be delayed?
Yeah, so you can imagine, so that statement inherently is a bit gauge dependent statement, but let's imagine that you take a picture of just the homogeneous evolution during inflation. So you say you have some potential, some roll potential, and the field is rolling, and you say there is some field value. When the inflaton crosses that field value, maybe the slow roll parameters become large, so inflation would end. So this is a picture which is valid at the homogeneous level, no mention of fluctuations. So now imagine you have some particles, heavy particles. What they're doing is that they're dragging the inflaton back. So if you imagine the evolution of the inflaton field in those locations, because of the drag, they would cross the threshold a bit later than usual. Because it's just slower. Which means if you focus on other regions where this particle is not present, in those cases, like inflation has ended, you are, let's say, in radiation domination. But in this location where it's slower, inflation would last a bit longer. And roughly you can imagine it's some sort of CC dilution, which means those regions would have more energy density compared to the neighboring regions, because those have started diluting earlier. Which means, like, wherever these particles are, you have some localized overdensity. And that translates into having some gravitational potential.
So effectively, you have some friction when you produce those particles.
Right. I mean, yeah. So you can see this in different ways. One is you can do, for example, some in computation, and you can compute the 1-point function of the curvature perturbation due to this particle. The details are not super important, but you see like the same factor G appears. You can also study this by studying the equation of motion of delta phi, just Klein-Gordon equation, along with this tadpole type effect, and then you also see the same thing. Like you see that the delta phi has a modified expression, which is like you have this effect from the coupling. Okay, so here I'd like to just point out that there is another parameter that has come in, which is again expected, which is this eta star. This is the horizon size when particle production was happening, and it is just telling you that if you look at modes, which were super horizon during the time of particle production, they do not really get affected because of this production business, because they were just super large outside the horizon when all of this was happening. So in the k eta star going to zero limit, this term actually becomes very small. But then when k is of the order of eta star, or 1 over eta star, you are then focusing on modes that are exiting the horizon right at the time of particle production. And that is where you expect to see most of the effects. In other words, because of these heavy particles, you sort of affect a horizon-sized region centered around the heavy particle, you affect the perturbations in that region. And then what is important, all the prefactors are not extremely important, but you can actually take the ratio of this zeta due to particle production with the usual RMS fluctuation from just standard quantum fluctuations. If you take the ratio, you notice that the going rate is just G, like all the other dependencies, they effectively cancel out. So what that tells you that this coupling G, it plays the role of distinguishing how big these overdensities are when you are comparing that to the standard overdensities and underdensities that the standard fluctuations generate. In other words, if G is like a bit big, let's say 5, for example, then that would tell you that these overdensities are 5 times as large, and that potentially can give rise to an observational consequence. If these G is much smaller than 1, these effects, they are just swamped out by the standard fluctuations. They are just buried deep inside them, and you don't see them. Okay, so that's the main effect. And treating this, like for example, more technically, this guy as our starting point, you can compute a bunch of different effects. You can, for example, compute how the temperature anisotropies are affected, how we would modify the late time evolution, and how we would modify, for example, galaxy formation. But qualitatively, this coupling plays an important role, and we are always going to think about values of G that are somewhat larger than 1, because in that regime, these localized overdensities would sort of stand out above the ambient fluctuations.
I have a question. Sorry, could you explain the dependence on eta star again? having a hard time sort of visualizing it.
Right. So sorry, this is some sine integral function. Is you integrate over sine x over x.
Okay.
But effectively it's some trigonometric thing. So what you should imagine, you can take the limit where k eta star is going to 0. So eta star is the horizon size. So k eta star going to 0 means you're focusing on a mode that is much larger than horizon. And you would expect, just because of causality, that those modes are not going to get affected because of particle production, because they're so big. And in that limit, you can indeed show that this function, it falls off polynomially, so it is very small. But what you would expect naively is, if particle production is happening, the modes that are of the size of the horizon, they would feel the effect, because they know causally what is going on, that there is something non-trivial going on within that horizon. So you would expect when k eta star is of the order of 1, there is some non-trivial effect, and that's, this function is order 1 when k eta star is order 1. So, yeah. All right. So far, what I've argued is that you can produce particles that are much heavier than Hubble during inflation, and even though these are very rare, they're individually pretty striking, and they can give rise to localized overdensities around their locations. Okay, so these overdensities would then, of course, evolve in non-trivial ways as we move forward with the evolution. So that's what we are going to discuss next. So I'm going to briefly discuss what happens in the case of CMB, and then move to galaxies. All right. So once again, this is a picture plotting the gravitational potential as a function of position. Now, that was the picture during inflation, if you want. So after inflation ends, let's say the universe is filled with some thermal plasma, but you have some gravitational potential well over here, which means you have more plasma that is trapped compared to neighboring regions. And that means when CMB decoupling happens, this region would emit more photons compared to the neighboring regions, which means if you are to make a scan of the neighboring regions and this regions, you will see more photons coming from this region. In other words, you will see a bright spot on the CMB. Okay? So this is the basic idea. In a cartoon sense, this is how the sky would look like. So this is like a blank sky. So I've switched off the standard CMB. You would notice that there are certain random bright spots on the sky. The locations would denote wherever initially these heavy particles were after they were produced. In this particular model, I have a coupling which is like phi squared chi squared. So that would mean that you always produce a pair of these particles. Just by momentum conservations, you tend to see pairs of hotspots instead of single spots. But they can also sometimes overlap, so they can effectively give you a single spot. But a priori, you would expect 2 of them.
All right, these things, the size of these spots are
I'm going to come to that in a
smaller
second.
than the horizon size at the CMB, or
They're related. They're not much small. So I'm going to show you
okay.
profiles literally now. So.
Okay.
So it depends a bit on the transfer functions, but that's entirely lambda CDM effect. So here what I'm doing is I've zoomed on in one of the pairs here, and you see like this is how it might look like. So I'm plotting temperature here. So you can have like 2 bright lobes, and then the associated shape. But the good thing is that if you focus on one spot here, how the temperature varies as you move from the center to the periphery, you can actually compute it. It's entirely a lambda CDM effect. We know what the primordial curvature perturbation is. You know when the modes re-enter the horizon, you know what the transfer functions are. So you can just compute the radial profile. So this is, for example, what happens if eta star is like some number, let's say 160 megaparsec, and then 2 more choices. And you see like the angular profiles, they are a bit different. And this difference entirely comes in because the modes associated with these eta stars, they re-enter the horizon at slightly different times. So the subhorizon evolution is a bit different. But roughly speaking, they have roughly the same feature, which is like as you move from the center, you have a falling spectrum. So, so that's, to answer your question, on the sky, roughly speaking, if you for example take this example, so this roughly corresponds to, if you want, a degree, I think, and you can sort of imagine a rough size of this spot, which is of this kind. So there's some order 1 factors here, but you can compute them. But roughly 100 megaparsec would be like a degree of the sky. So that's your angular size. But since we can compute these shapes, we can actually learn a lot about, we can actually look for them.
If these spots are already inside the horizon before CMB, if they are,
Sorry, is this?
if those overdensity region
Uh-huh.
are really inside the horizon during radiation domination, do they get washed out, and do they, because of the thermal?
So they start super horizon.
They start super horizon, yeah.
Yeah, but then you have some overdensity, and you can, if you want, you can Fourier decompose it. So you have some overdensity in position space, then you can Fourier decompose it as a function of k, and then you can track each of the individual k modes, because they of course like exit the horizon like usual, and then they re-enter the horizon.
I saw the interhorizon during CMB, right? What's the horizon size during CMB?
Yeah, that's what I was.
You mean CMB decoupling or?
No, the horizon size during recommendation. I remember it's something like 1 megaparsec.
I think that should be, that should be around
And this is a bigger,
like L of few hundred,
a few hundred.
yeah.
So these things are much bigger than the horizon size.
They're not bigger, but they could be much smaller also, yeah.
But smaller, I would say, wouldn't they be washed out a bit because?
Yeah, I mean, so good, so maybe this picture is useful. I think maybe this is what you're asking. So let me just, let me explain the figure and then go over the other stuff. So imagine that so this is us, observers, and then this is the decoupling surface. There's some finite thickness, which is like order 20 or so megaparsec for the CMB surface. And we are in some sense looking at, so there's some co-moving diagram. So we would be most sensitive to overdensities that are within this shell. If something was too far away, then those would be all washed out because of the oscillations. So you're kind of focusing on the region. I mean, if you take the ideal limit here, the infinitely thin limit, you're literally looking at the spots that were directly on the CMB surface when the decoupling happens. Because if you take something that is too close to us, then it has nothing to do with the CMB. Like CMB has already decoupled and it's not interacting. If something is too far, then the photons, they have already scattered a lot before getting decoupled. So again, you lose the information.
Yeah, they probably will wash out.
That's right, that's right. But if it is right at the surface, then you get to see them. Then of course you can compute like how many of them are actually there, because there is some finite thickness. So what you can do, you remember that we had computed the number density. So you can of course, you need to dilute that number density from the time of production till today. And then you have to multiply by some volume here. And if you take some example numbers, for example, some coupling of 3, some eta star, and some minimum mass, which is 250 times Hubble, let's say, within the shell, you would expect to see like order 25 of them. So that's one benchmark number.
But what's the mass of chi in this case?
Depends on the Hubble.
Okay.
So
how many times the Hubble? Oh, this M0 is the mass? Or?
M0 is the minimum mass.
Oh, it's the minimum mass. Okay.
Right. I mean, they get much heavier because the other mass is dependence on G times phi. So yeah, this is the minimum. Yeah. All right. So just to summarize, so these 3 model parameters, they are connected to 3 observable parameters if you want. So of course, if you crank up G, the overdensities are larger in magnitude. So the central temperature of these pixels, like these sort of central temperatures, they also go up. So in that sense, hotspots are easier to see if you take larger G. Eta star roughly determines the sizes of these spots. And M0, it determines how many of them you'd expect, because of course the total number is exponentially sensitive to M0. So from a search perspective, this is what you need pretty much. And then if you want to actually do the search, the questions you would be asking then is very similar to like recognize the CMB with and without hotspots, right? So this is one example. So I have two images. One of them has hotspots hidden inside it, the other one doesn't. But you see, like they pretty much look the same. But in secret, the figure on the right, it has 3 pairs hidden because I've generated this mock data myself, so I know where they are. But the goal is to just like if you want to do a search like this, you want to develop a technique that can isolate these localized spots. And this is something that cosmologists are doing for a very long time. You can approach this problem in different ways. One standard technique is to use a match filter analysis, for example. So I'll be a bit brief over here because I'm slowly running out of time. But the basic idea here is that because you know how these things look like, you can develop a filter. And then you can perform a convolution across the entire sky. And then after performing the convolution, you would hope that the locations where the spot is would be sticking out, would be standing out, right? So here is, for example, one case study. So you have a pair of hotspots. This is the MB and CMB without any hotspots. So what you do is you develop a filter based on the structure. Then you can inject this guy over here, and then you can perform a convolution. And if your filter is good, then what you would see is that on the filtered map there would be like 2 pixels that are brighter than usual. So in other words, this filter effectively changes the contrast of the image, and it lets you detect otherwise hidden spots. But it's something very standard. People have been using this, for example, to detect various thermal SZ clusters. And basically utilizing that pipeline, we did a search with the Planck data. I won't be getting into all the details here, but the quick upshot is that the search can be done. In fact, based on one analysis, you can even find several potential hotspot candidates. You can even like plot them. You can plot a histogram as a function of the signal to noise. So you might be happy for a second because here you would see like there are lots of high SNR candidates. But it turns out if you apply the same technique to the component separated Planck maps, where you have done a better sort of subtraction of the various astro backgrounds or foregrounds, you'd actually find all these candidates they're absent. In other words, with this analysis, we didn't find any hotspots, unfortunately. But the upshot here is that these searches can already be done with the existing data. So if we analyze the CMB, or if we look at the CMB with a better resolution instrument, in principle, we can do better. So just to show like a parameter space here, the region of the parameter space you can constrain right now with this particular search is interesting, but I won't say we have hit the theoretically interesting target yet. So here is, for example, this coupling G as a function of eta star. And this gray area basically, if your model parameters were in here, then you would have produced just a single spot, but that individually would have been so bright that you'd have seen it in the data. Okay, so this region is constrained by just looking for a single bright spot across the entire sky. And just to give you some example of what is happening with the mass scales, we can, for example, look at the green line here, where the mass is 1,000 times larger than Hubble. And then above this solid line here, you would predict, when you just you follow the formulas, you would predict that you would expect at least 1 hotspot in the sky. And then below this dotted line, the back reaction on the homogeneous inflaton dynamics is sufficiently small. So in some sense, within these two lines, you are in good theoretical control. But then what this search is telling us is that effectively this part of the parameter space is ruled out. Okay? You can of course have things here, but then that would basically mean that you are looking for eta stars which are of the order of 10. So they are much smaller in size, and effectively you run into the noise and the resolution of Planck. But in principle, this is something that can improve in the future if you go to a higher resolution instrument. But this
Can I just ask a clarification question? So you're saying given mass and the eta star, you can actually predict the G and which will be.
No, so these are all independent. So what I'm saying here, so this search was carried out looking for just one spot in the entire sky. And because M0, it tells you how many of them you produce, this search was a priori insensitive to what M0 was. Okay, because the sizes and the brightness of the spots, they are just given by these two. So from an observational perspective, you only need these two parameters. But then M0 comes in because let's say you choose such an M0 that theoretically you don't even expect one spot in the entire sky. Then the search doesn't apply. So that's where these things come in. So here I'm saying, if you have a particle whose mass is 1,000 times larger than Hubble, then below this line, you don't even produce one hotspot. So the search is not even applicable here for the green region. And above this line, you start modifying the inflaton dynamics. So you have to do a better treatment. So it's like a dashed line if you want. So it's subject to theoretical improvement. But within this region, you are in good theoretical control, and you have produced more than one hotspot. But because you didn't find even one, that region is ruled out. All right. So we of course do not know what the Hubble scale during inflation is, but this example, it tells you that, for example, if Hubble is around 10 to the 13 GeV, in principle, you're probing particles that are extremely heavy of the order of the Guts scale. So in that sense, it would be exciting to sort of redo these searches if we get more data, and also of course better instruments. But then in some sense, we also want to push to smaller values of eta star. Fundamentally, of course, CMB would be limited, but that is where other observables, such as galaxies, can come in, because these are overdensities, and even if the hotspots are too tiny in size, they can still affect how matter and everything else clusters later on. So these hotspots, even for these much smaller values of eta star, they can affect structure formation. In particular, they can give rise to, they can modify how galaxy formation would typically occur in the context of lambda CDM. So using that approach, you can actually go to smaller values of eta star. But this is something we are working on right now. Hopefully the paper will be out soon, but some of these results I'll show will be a bit preliminary. So yeah, in the remaining 10-ish minutes or so, I'll briefly go over this. And then yeah, we can discuss it. So again, just to clarify, I'm switching gears here. I've been discussing about the CMB, but now I want to probe much smaller scales. So that is where galaxies are useful, or generally just over densities in the dark matter field. And in some sense, like a priori, this requires a pretty intensive numerical approach, because what I'll be showing is that these overdensities, they modify galaxy formation, which is intrinsically a very, very nonlinear process. But you can make a lot of progress by doing the sort of semi-analytical pressure type analysis, which says that if you take some random realization of the density contrast as a function of position, then you can figure out certain regions where the density contrast goes above some critical threshold, which is like 1.68 or so. And according to the semi-analytic formalism, above this critical threshold, you can mark out the regions, and in those regions will eventually collapse to give rise to halos. And those halos would eventually host galaxies and so on. Okay? So it seems like, a priori, it seems a bit ad hoc, but it turns out that this prescription with some more additions. It works amazingly well, and you can match a lot of the n-body dark matter only simulations pretty well. All right, so we'll be taking this kind of an approach, but pictorially, why you would expect a modification in the galaxy formation aspect can be illustrated very simply. So let's just imagine a lambda CDM story first. So I'm focusing on a single K mode, and I'm studying its evolution as a function of the scale factor. Now, during matter domination, these modes, they grow linearly with the scale factor, which means if you start with some small value, eventually there will be some redshift where this passes this critical threshold of like 1.69 or so. And that means that in a region associated with that K mode, there would be a halo formation. And of course, you can evaluate all of this by taking the standard transfer function, some growth factors, and things like that. But in this case, there is one major difference, which is your overdensities, they start out by being larger, right? They're larger by a factor of g, but everything else is pretty much the same. So you have the same evolution. So things grow as a function of linearly with the scale factor, but because they start out larger, they would hit this critical scale at an earlier redshift, which means for a given halo mass, the associated halo would appear at a much earlier redshift compared to lambda CDM. So that's the main effect. So you give rise to massive halos at an earlier redshift compared to lambda CDM, and that would give you interesting observational handles to look for these effects. So yeah, I'd be a bit brief here, but just like how we can compute the temperature profiles, you can compute the overdensity profiles from the inner region to the outer regions. And these kind of analyses, they can actually tell you what kind of halos would form at what redshift. For example, so of course halos, they keep on merging, they get bigger and bigger with time, but this kind of picture, they can tell you, for example, at redshift of 16, for some model choice, you'd have a halo which is of this kind of mass, and then as you go to later and later times, the halo would grow to have this kind of masses. But I won't be going over this in too much detail. What I would like to just point out is that many of the analyses, they go in parallel with the CMB. For example, you still see that there are these three parameters that basically describe a lot of the physics. For example, the number densities of these early halos or rare halos, they would be given by M0, again, because of the exponential sensitivity. This thing would govern when you start forming them. And then eta star would roughly give you how big these are, or in other words, it would give you, it would let you estimate the halo masses. So the observables here would be the halo masses, the redshift when they appear, and how many of them would appear. And then using this, you can construct observables. So there's one fine point here, which is, so this is something which is a bit different from the CMB. So one thing that can happen, because you have an ambient Gaussian field, is that in some cases, the heavy particle induced overdensity, they would sit on top of a lambda CDM overdensity, which means the net overdensity is even larger in magnitude. And that would mean that the collapse would happen even earlier. But in some cases, it would sit on an underdensity, which means the collapse would happen later than usual. So what that would tell you is that there is some inherent spread that would happen in the rare galaxy formation just because you're sitting on an ambient Gaussian random field. But you can estimate like how big this spread is. For example, this particular example, you would expect rare halos around 12 plus minus 2.8, roughly speaking. This is a very simple treatment, but it sort of tells you how many rare halos to expect if a survey focuses on a given redshift with some window in the redshift bin. And the reason why this can be connected to exciting observations is because as you might have heard, various surveys with the JWST, they seem to be saying pretty high redshift and very massive galaxies. We actually do not know where these are coming from. This could be entirely astrophysics. It could be BSM. We do not know for sure because star formation at these very high redshifts are not well understood. Just to give you one example to show this tension, if you want. So this is from this reference. So here what they're plotting is the stellar masses, which is related to the halo mass with some factors here, which is related to the star formation efficiency, how much baryons there are, and so on, as a function of redshift. So you can plot, you can make a plot like this, and then what this tells you is that if you focus on this particular line over here, it corresponds to a number density of 10 to the minus 7 inverse megaparsec cubed, which means if you had a survey whose volume was 10 to the 7 megaparsec cubed, then on this line, you have seen exactly 1 halo. Okay? But for this particular survey, the volume was actually even smaller. So on this line, you would have actually seen less than 1 kilo. But what they saw was that there are at least 3 candidates, or even another one here, that are above this line. So naively, what it tells you is that halo formation was much more efficient compared to lambda CDM if you take these kind of star formations rates to be valid at these redshifts. So that is the puzzle. We actually do not know what is going on, and of course, this will get improved as we make better observations and improve the theory. Yeah.
Can I ask a question?
Yeah.
So what they're doing here is you map stellar mass to halo mass and use the number CDM halo mass function to calculate the number density.
That's right.
For the most extreme stellar mass, do you actually start to touch the exponential tail of your pressure mass function, or that's still in the power law regime?
No, I think this would be in the exponential regime.
It's still the it's gonna be.
I mean, this is all like this is the end, like the cumulative number density. So in some sense, it's already encoded. The press sector mass function is encoded.
I see. So they're already pretty rare halos.
Right.
So
the main uncertainty here is in this number. So what this number is telling you is that if you have 10 baryons in the halo, only one of them goes to forming stars, right? So like not all the baryons are in stars, right? We don't know what this number is. This is one expectation. It could be a bit larger. It could be 0.3, 0.4. We don't know. But 1 is of course the theoretical limit. So if you were to crank up this number by a lot, like if you make it like 0.4, 0.5, which is still very, very high efficient star formation, then you would actually find that these lines would move up or these can equivalently come down. So then you won't say that it's in tension. So, but the main uncertainty here is that we don't know what this number is. So in this particular paper, which is very nice, they give you several examples. So
if we consider to be a redshift and halo mass independent, okay, can it still depend on those parameters?
So what you can compute from the mass function is that they're not completely independent, right? Because at a given redshift, you know how like what fraction of K modes have become nonlinear given lambda CDM, and each of these K modes would give you a certain halo mass, like some mass in the collapse structure. So they're not completely independent, and that information in some sense is like if you move all the observation points from here, those informations are in these lines. So they tell you for example, if you take this point, it will tell you like at a redshift of 14, if you have a survey volume, which is like 10 to the 7 megaparsec cube, you'd expect 1 halo with this given stellar mass. So if you were to take this at the face value, and if you trust the star formation rate, you need something beyond lambda CDM to explain this. And people have been trying this for a while. One thing that people did try was that maybe there is some bump in the primordial power spectrum, and that would give rise to like rare halos at high redshifts because there is more, like the power spectrum is larger, so there is more structure. But then there is this interesting paper which showed that if you do the kind of modification, or if you start putting bumps on the power spectrum, then under certain classifications, they actually can mess up with other observations. So typically these sort of broad modifications, they do not work. You would be in tension with other data sets. But the good thing is that the kind of scenario I've been talking about, these are very, very rare processes. So you don't modify the power spectrum significantly. And here's just to illustrate like one potential data point here, right? So I'm drawing the same figure as before. Again, these lines are from the lambda CDM halo mass functions. Again, this is the star formation rate. And these are the observation points I was showing in the previous slide. So the star here is corresponding to one benchmark point. So if you take these kind of numbers here, you'd predict that at this point, you would have like at redshift of 12, a certain halo mass, and this would be the number density. And if you compare this number density with the contour here, you would conclude that this is really 10 or more times the number of halos compared to lambda CDM. In other words, these kind of rare production scenarios, they can tell you that on certain localized redshifts, you expect many more halos compared to lambda CDM, and that could potentially give us some idea in the context of this puzzling JWST observations. I'm really out of time, but so let me skip over this. This is just to illustrate that you can actually compute what the correction to the matter power spectrum is, and for this type of benchmark points, they're pretty small. So effectively, you don't probe them by looking at the power spectrum. All right, so let me pretty much summarize here. So this part of the story was to tell you that these rare processes, they can modify early galaxy formation with a very small modification to the power spectrum, so they are potentially interesting. And to broadly summarize, these kind of scenarios, you're like from a particle physics perspective, you're sensitive to very, very heavy particles. They can give rise to a variety of signatures, for example, hotspots on the CMB, or they can give rise to massive early galaxies. We can already do a search with the Planck data, as we have done, but then this can improve in the future with more data and better instruments. But then you can also potentially look for these things with the high Z or deep galaxy surveys. So that would be interesting to do. And I've been very agnostic about particle physics models because I've taken it to be just some generic particle. It would also be interesting to sort of construct inflationary models where this can happen, because then we might get some clue about what the masses could be, what the couplings could be, and so on. So yeah, so that's pretty much it, and let me end here.
Any questions?
Yeah, that's a question. Can you go back to your power spectrum plot, even though you're saying it's not important? So,
This one you mean? Or?
yeah, this one. So you only cut it off. You cut it off at 10. Is it possible? What's the behavior when you go to even higher K?
I mean, it just keeps falling. So this, I should clarify, this is not the matter power spectrum. This is the primordial power spectrum.
Yeah.
What I'm plotting here is the ratio. Is the ratio of the particle production induced power spectrum. Because what I showed you was like brimming of one inflaton, but you can have brimming of two inflatons, so that gives you a 2-point function. So I'm comparing that with the standard. So it's just the ratio, and the ratio is is super small.
I see. It's just a tiny bump on top of the primordial.
I mean, you won't see it if you were to just. I mean, that's why I'm plotting the ratio. It's just a very small bump. Of course, all of this depends. I mean, the intuition here is that when you do the power spectrum, in some sense, you're doing an average over the entire sky. So if you start producing many of these things, right. So if you reduce M0, then you start to see an effect.
I see.
So the power spectrum is sensitive to how many of them you produce in total.
How many hotspots you have.
Right, how many hotspots or how many galaxies, for example. But the point here is that when you're looking for individual objects, you're searching for only one of them. So you can be in a regime where things are very drastic by like individually, but there are only a few of them. So in that regime, you don't modify the power spectrum, but of course, the good thing to do is to just go and look for it in the position space because you are looking for individual objects then.
That basically means you're super non-Gaussian and the power spectrum is no longer a good measure.
You would be super non-Gaussian in those regions, yes.
Right.
But I mean, our standard analysis, we are always doing an average, right? So that's the,
That's right. But does that mean you also, it's pretty challenging if you only have a few hotspots to explain those early galaxies because you still have a coincidence problem there.
right, I mean, yeah, so it depends on, right, so it depends on, I think the story is far from over because we would need to also understand the astrophysical aspects. But yeah, I mean, so you know, a given survey, you know the volume. So, I mean, you know how many things you would expect
Right.
given some BSM model.
Yes.
So, I mean, in this particular example, they were seeing only a few, right, above this line. There are many things over here, right, in this gray region. But you're looking at the tails, you're looking at the outliers. So, yeah.
Thanks.
If I were to think about lower scale inflation, that comes indirectly into your parameterization by making me go to larger etas? So, or does it not change at all?
Yeah, so you're mostly sensitive to just the ratio of this M0 over Hubble.
Okay, so you're just focusing because it's exciting to.
Yeah, I mean, if
scale
it is high
physics?
scale inflation, it's exciting from a particle physics standpoint, but you also don't know what the spectrum is over there. So,
Okay.
I mean, if Hubble is 10 to the 10, then these masses are like 10 to the 12, 10 to the 13, but maybe there is something interesting from a particle physics side.
Right, but even, let's say Hubble is, or wow, temperatures of a GeV or something, I want to.
Yeah. Yeah, I mean, then, yeah. All of these would work totally fine.
Okay.
Yeah, because you're just sensitive to the ratio.
Okay.
Yeah.
There are no more questions, let's thank our speaker again.